when I was in my teenage years, I didn't really know what I was going to do. The fact that I was 15 when I got very seriously interested in electronics in the 1950s, that shaped my entire career. I was extremely fortunate that that happened to me. And because when I went to university, a lot of young people my age at the time were still confused about what they wanted to do with themselves. To me, it was very clear. And it was because of an experience I had, quite by accident. I didn't tell you the story of how I got interested in Gordon Daniels' electronics next door. It was because this little airplane I used to shoot up on a slingshot used to end up on his roof. I had to negotiate to get it off. And in making peace, I learned about electronics that he was doing in his basement.
At what age was that?
I was 15.
Hi, I'm Jason Robinson here with John MacDonald, founder of MDA, MacDonald, Dettweiller and Associates. And John's going to tell us a little bit about his passion for technology and how he ended up here at MDA.
Well, there's the MDA story, there's my story as a university professor, there's the Day 4 story, and how it all started when I was 16 years old.
Wow. Please share with us your road to technology.
Well, it started when I was 15, actually. Our neighbor was in marine radio telephone business. Now, this was back in the early 1950s.
Okay.
And I was still in high school. But I became very fascinated with what he was doing. He was building radio phones for boats, and mainly fish boats, but there were some shore-based systems as well. And he made them in his basement and rented them out. It was quite a good business. And I became fascinated with all this. This was really the beginnings of electronics. I mean, it's come a huge distance since then, of course, but we used vacuum tubes and whatnot, and I learned how to build these things. I learned how to service them. Mm-hmm. And as things worked out, the person I worked for, his name was Gordon Daniels, and Gordon wasn't well. He died relatively young in his late 50s. But what had happened at that time was that the government had changed the tolerances on the frequencies for the shore stations.
Okay.
And some of his stations were out of tolerance because they'd reduced it to half what it had been. Okay. And somebody had to go down the coast, and I was living in Prince Rupert at the time. And these stations were all the way down to Namu, which is just north of Queen Charlotte Sound. So anyway, I had, as a young child, been down there with my father because he was a master mariner. And so I was familiar with the area. So basically I went on a servicing expedition to bring all this stuff back onto frequency at age 16.
Wow. Wow, what a great opportunity.
Well, it really was the beginning of a fascination with technology. And of course that's broadened since then. I was having a whale of a good time. I mean, I just really enjoyed my job. I was very young, and I basically hitchhiked down on fishpackers.
Oh, did you really?
Oh, yeah.
Wow.
And because, you know, my dad took me part way, but, you know, he couldn't go all the way down. And I had to stop at various places, logging camps and fish camps and one thing and another, and boats and so on. But I was familiar enough with the area that I didn't get lost or anything like that. Yeah. And my mom said something to me which was some of the wisest advice I'd ever had, and that was, look, if you want to make a career of this, you go to university. And I had no particular idea of going to university up to that point in time. Sure. As I said, I was having a whale of a good time, doing this.
Yeah. How long did that take you to do the refurbs on all the pieces of equipment?
Oh, it would be sort of a day per station.
Okay. So
there was a couple of times when I had to wait for parts that came too, so I was there for several days waiting for things to come from Rupert. And I remember one time there was this rather luxurious American cruiser came in, and I was just sort of hanging around on the floats, and I helped tie him up, and he said, "Where's the radio man?" I said, "You're looking at him." This 16-year-old kid. Anyway, I fixed his radio. It took 10 minutes.
That's great.
That's great. And so anyway, I went on to UBC and took engineering, decided to go to grad school, qualified to go to MIT.
Good.
And I wanted the best engineering school in the world, and
Absolutely.
At that time, I guess it probably still is. And I did my graduate work there at a master's and a doctorate.
Okay.
And I really had trained myself by that time to be a professor, to be a teacher.
Right.
And that was my vision of my future career, do research and teach. I was relatively good at teaching, I've been told. And so I was an instructor at MIT before I finished my degree, which is the most junior of the faculty positions. Yeah. And after I got the doctorate, then I became an assistant professor at MIT. Okay. And I was there for another year and a bit. And I got an opportunity to come back home, and a friend of mine who used to visit me when I was at MIT said, "The thing about you guys from BC," he says, "any time I meet you anywhere in the world, you're always on your way home." And I kind of fulfilled that prophecy. I mean, I accepted a job as a professor at UBC.
Oh, good.
I was there for 7 years.
Yeah. Well, Vancouver's not a bad place to
it's a great place to call home. Anyway, while at UBC, I discovered something about myself. I was built to create things that worked and contributed to society.
Okay.
And when you're teaching grad students, I mean, they're all great and you do wonderful things, but you're not creating a system that is used. You're teaching a person, or you're teaching a group, or that's your job, and I enjoyed that. I still miss the students. I don't miss anything else, but I do miss the students.
But you had a creative side to yourself as well.
Oh, no question about it. Yeah, that I guess is probably my main skill. I don't really know, but I certainly do have a creative bent. There's no question about that. Anyway, I had met Vern Dettweiller. You said I was a founder of MDA. I'm a co-founder.
Right.
But Vern and I had met when we started university, because Vern grew up in Smithers.
Oh, okay. Up north as well.
Up north. Oh, yeah, we're both from the north.
Nice. So
it's kind of appropriate that today I'm the Chancellor of the University of Northern British Columbia. but anyway, I had always gone up and down the coast on a passenger ship to come to Vancouver.
Yeah.
And this was the Christmas of my first year at university. I'd just finished my first term. I said, I'm going to go on the train. Oh. I've never done it before, and my grandfather had been a conductor on the CN from Smithers to Rupert.
Wow.
When I was growing up, although he'd been in other sections of that area before I could remember. But when I remember him, he was a conductor on the passenger train from Smithers to Prince Rupert. That was his part. Anyway, I got on the train, headed for Rupert, and I met Vern on the train because he had to go to Smithers.
Okay. Okay. That's how it happened.
That's how it happened. And
the universe put you together.
Yeah. And so, you know, we both went through university and so on. And then I went on to grad school. But Vern, at that time, that was the beginning of computing.
Okay.
Really.
Yeah.
I mean, you were dealing with what today would be laughably primitive machines. But he went into the computing center when he graduated. Okay. Before he graduated, I mean, he got fascinated with that.
Yeah.
He was incredibly good at it.
Wow. Okay.
And I went off to MIT, but when I came back, I was now a professor at UBC. Vern was a senior guy in the computing center. And we started talking about what you could do with the company. Mm. And I wanted to do that, and so did he. So in 1968, we formed MacDonald Dettweiller. I had a little bit of time finding the name. We finally used our own names.
When all else fails.
Yeah, and you know the funny thing was, at the time I thought, oh, we'll have a problem with that because this country's full of McDonald's, you know, there'll be some kind of a problem.
Sure.
It turned out that we got the name, provided we didn't interfere with the business of the three companies in Ontario that had Dettweiller in the name.
Oh, not the MacDonald.
The MacDonald didn't seem to bother
really?
anybody.
Wow.
The way we started was, it was a time in the late 60s, early 70s when real-time software was new. Mm. Okay. For controlling systems and all that. It's commonplace today. I mean, do it that way everywhere. But, right. But in those days, this was new.
Yeah.
Vern wrote a very clever real-time operating system. It was as fast and responsive as it could be with the technology at the time. And our first job was with a company called Lenkert Electric, which is no longer here. It changed over time and so on. We did the software for the Northern Interprovincial Radio System, which was a supervisory control system for monitoring and controlling what in those days was the second microwave link across Canada.
Okay.
And the southern one was the first one. It was already in existence. And now in the late 60s, early 70s, they were building the northern one. It went up through Fort St. John, I think, into Alberta, down by Edmonton, and went across that way.
Okay.
And so
now there are
satellites and fiber optics and all that. You know, I mean, but that thing was entirely computer based. Wow. And basically, Lenkert came to us and said, you know, basically their competition was advertising that they were going to do a computer-based supervisory, which was a new idea. Mm. The way it had been done before was all with hardware and buzzers and lights and bells and to alert people if something went wrong. And they had no idea how to do a real-time system.
Right. Yeah.
And well, they asked me if I could do it. I said, sure, I know how to do that. Yeah. And got together with Vern and a couple other guys, and we formed the company. That's what we did. And the entry into space, of course, I had one thing I recognized many, many years later. I was sitting in my office at MDA. It was a couple of years before I retired, the first time. I've retired twice in my life. I retired 3 weeks ago. Okay. For the second time. I'm not sure how long it'll last, but anyway, I'll try it again. And well, you're in your late 70s, you know, it's time to think about that kind of thing, I guess. Anyway, I was sitting in my office here at MDA, and I suddenly realized something, because we had made a huge contribution to the whole field of observing the Earth from space. Mm. And I suddenly remembered that when I was a little boy, long before this excursion down the coast to fix radio telephones, I'd wondered what the Earth looked like from space. Mm. And I suddenly, it was a kind of a point in my life I'll never forget. I said, my God, that's what I ended doing. That's what I ended up doing, was developing that technology. Or, more precisely, contributing to the development. No,
Right, yeah.
that's not something you do by yourself. But,
No.
but
But it all starts with an idea.
It starts with an idea,
with
absolutely.
the cognition or the thought of
Absolutely.
what if.
Absolutely.
Yeah, yeah.
And I think I was probably 5 or 6 years old when I had that idea. I thought, wonder what it looks like from space. I never went up there. I've known several people who did, but I did it. I helped to develop systems that were the first systems to look back at the planet in any kind of detail.
Wow.
And I was kind of struck by that. Anyway,
that was the foray, the first venture into space.
Yeah, and then what happened was, I guess it was 1970 or 71, a good friend of mine, Dave Sloan, who unfortunately passed on a couple of years ago. Dave had this fascination with space and observing the Earth and all that. Okay. And he wanted to do this, and there was an opportunity to build a part of a ground station for what ultimately became Landsat. It was called ERTS-1, Earth Resources Technology Satellite in those days. And it launched in 1972, and this was 1970 or early 71. Okay. And what happened was they put out, the government, it was the Department of Communications at the time, put out an RFP for 2 systems. One was a demultiplexer for the ground station, which is, in those days, the downlink bandwidth was somewhat constrained. I mean, this was the early days, you know. And so
infinitesimal compared to today.
Well, yeah, and so and the recording system was these gigantic tape recorders. They had, you know, reels like that and 28 tracks and whatnot. And this device was to take the downlink signal and distribute it across those 28 tracks in a way that you could retrieve it to build the images. And that was called the demultiplexer. The other contract that was available was the whole processing system for all of this. Okay. Anyway, we won the demultiplexer and lost the other one. And the government people, I think they were a little nervous because our competition was Hughes Aircraft.
Oh, really?
Oh, yeah. We beat Hughes on the basis of technology and price.
Wow.
And it was the early days of integrated circuits. We used integrated circuits, they used discrete design because that was what had gone on up to that point in time. But we took the leap into using integrated circuits. They were, by today's standards, again, relatively primitive integrated circuits, but nevertheless, it was, you know, more than just a transistor on a chip. It was a little circuit on a chip. Yeah. Called MSI, medium scale integration.
Okay.
Anyway, we...
I was born in 1970.
Were you?
I was.
Well, there you are. Good things happen around 1970, I guess. So, anyway, we built this thing. Yeah. Worked like a hot damn. We built it in a box that was actually supplied to us by a mini-computer company. Oh. We put it in order for the box alone. We didn't need the computer guts because we could put our own guts in the thing, which we did. The thing was designed in a way that you could put a circuit on a big board like this and just slide it in, and that meant we didn't have to design hardware to house the thing and everything. Anyway, it worked very well. Nice. And we had an idea. It was really Dave's idea, I think, and that was to develop a system we called a quick look system, because the way the thing operated in those days was there was no intrinsic imaging capability at the ground station. They just filled the tape, sent the tape off. In the case of the States, They sent it off to NASA. In the case of Canada, we sent it off to Ottawa.
Right.
And somebody processed it over there to get an image out of it. The guys at the ground station had absolutely no idea whether they'd made a tape that was worth anything or not. I mean, they just put the data on it and hoped for the best.
Yeah, sent it away.
So we came up with an idea of a very small system that would make an actual image.
Okay.
Because to maintain the system, if you're going to find a problem with it, you're going to see it on an image. That's the way to do it. I mean, it takes you 5 minutes to look at the thing and decide if the data's half decent or not.
Yep.
So anyway, we built this thing, and of course it became a standard. And the cost of an MDA ground station for that type of thing in those days was pretty modest compared to what NASA was doing.
Yeah.
And so that was the beginning of MDA, MacDonald Dettweiller, becoming the chief supplier of Earth imaging, civilian Earth imaging ground stations in the world.
Right.
It was marvelous. I mean, what we did, the first station, well, the first thing we did was we put, the Canadian government had started something called an unsolicited proposal program. Now this thing, of course.
Is it like an RFP or?
Well, no, it was interesting. Of course, it got killed later on. You know, governments don't continue doing things for very long.
More than usually one.
More than a couple of election cycles.
Exactly.
But anyway.
The reality.
Yeah, it's a reality of life. Anyway, they had this unsolicited proposal program. They had a fund. This was 1972. They had a fund that a company could propose anything.
Oh, wow.
There was the way the government was organized in those days, it was the Department of Supply and Services. They were basically the government purchasing department.
Okay.
And they had a scientific part to them. And you could put in a proposal to do anything. And DSS, as it was called in those days, would shop it around to the various departments, see if anybody wanted to do this. And at the beginning, DSS would fund the whole thing.
Really?
Yeah, that changed, of course, very quickly. But
it sounds like a brilliant idea, though.
It was. It led to a number of things. Well, we put in a proposal to design a complete ground station and supply it to the government. And the need for it was that the first ground station that we'd done the demultiplexer for, was in Prince Albert in Saskatchewan. It did not cover the Maritimes.
Oh, really?
Because it was too far west.
Okay.
We put in a proposal to develop a low-cost ground station.
Right.
That would cover the East Coast.
Thanks.
And the interesting aspect of it was that the price for the ground station was $2 million. Now, up to that point in time, NASA was telling everybody that the ground station for this spacecraft would cost $25 million.
Really? Wow.
Yeah.
That's a huge cost savings.
Oh, yeah. And so what happened was, of course, by then the Canada Centre for Remote Sensing had been formed. And it was, had taken over the operation of the Prince Albert ground station and all that sort of thing. And by the way, the Prince Albert ground station, the reason it was in Prince Albert is there was already a station there for monitoring the ionosphere with radar. Okay. And so a lot of the antenna and a lot of the infrastructure was already there, and that's why it ended up there. The ideal position in Canada is Churchill, Manitoba.
Geographically? Or?
Geographically, okay. Yeah, because then you get the whole country.
Yeah.
We just had an oversupply of the Pacific Ocean from Prince Albert, but it was less expensive by a long shot, and so on. Okay. Anyway, we ended up building a ground station in a 10 by 40 foot trailer, and we put it in Shoe Cove, Newfoundland.
Oh, okay.
And it was there for many years, and eventually that capability was moved to near Ottawa. It would still cover the East Coast, of course, from there.
Yeah.
And
a little less of the ocean.
Well, yeah. Oh yeah, we see the edge of Ireland, I think. Anyway, that's how MDA started into the space business. What we did was we became the principal company in the world in supplying these rather esoteric ground stations. You know, when we supplied them outside of Canada, they were more expensive, but nevertheless, they never got to 25 million.
No, I guess.
And so we did that for years. But we kept innovating. We kept doing things that pushed the technology ahead.
Things that nobody else was doing.
Things that other people either thought was too risky. I've always had the attitude that if it's a technical challenge, there's always a solution.
I agree. There's always an answer.
Always a solution. Yeah. And if you can make it affordable, then it's a real solution.
That's right.
So what happened here was, first of all, we found innovative ways of making higher quality data, and so on. And of course, the quick look, as I said earlier, became a standard part of the station. But one of the major breakthroughs, and it led to RadarSat, was MDA got an opportunity to do the processor for a spacecraft called CSAT. Now, this was the first time that the Americans had launched a spacecraft in the civilian sector that had a synthetic aperture radar on it.
Okay.
It was a fairly primitive one, but nevertheless a synthetic aperture radar.
Okay.
Now,
for people who don't know what a synthetic aperture radar is.
Oh, okay. It's a radar, but what it does is, you find it in aircraft as well as spacecraft now. It flies along and sends a beam, a pulse, like a radar does, out to the side.
Right.
In its early stages of development, it wasn't synthetic aperture; it was just a radar, and it was called a side-looking radar in an aircraft. Well, the challenge here was to do a digital processor. And a guy by the name of George Haslam had this idea that you could do it digitally. And so he decided he'd go across Canada and see if he could find a company that could do this. Well, of course, he started, I guess, in Halifax or something, and eventually he got to Vancouver. He later told me, many years later, that the only company that understood how to do it was MDA.
Oh, good.
It was Dave and I, basically, you know, and we believed you could do it. Now, many people were of the view that this was just, if not impossible, it was at least impractical. Because the algorithms that are used to take that type of data and make an image out of it are quite complex. And as you fly along, you basically make the image by, in the along track direction, measuring the Doppler frequency of the return. In the range direction, which is perpendicular to the track, you are just doing what a radar normally does, which is measure the time the signal comes back.
Right.
But it's all a wide beam because you're 700 kilometers from the target if you're in a spacecraft. And so you have a wide beam, and you measure the position of anything within that beam by its Doppler return, because forward of the spacecraft and behind the spacecraft a little bit, you get a different frequency just with the Doppler effect. Anyway, That's about as far as I think I should go for a layout. Anyway, to take all this stuff and make an image out of it is not simple. And there were a couple of incidents. First of all, CSAT was built by JPL, the Jet Propulsion Lab.
Okay.
And we used to have
in
Pasadena, California. Okay. Yeah. And we used to have these funny meetings in the Bayshore Hotel here in Vancouver. The guys would come out from Ottawa, the JPL guys would come up from Pasadena, and MDA was here. Yeah. And we'd have these discussions about whether this would work or not. And, Dave had a very good justification. He says, oh heavens, he says, it's just radio astronomy in reverse. And it really is, because the technology is similar, except you're looking toward the Earth.
Right, yeah.
And
oftentimes that's what it is. It's being able to draw an analogy that people can get their head around.
And the type of processing that's done of data from radio astronomy is mathematically the same. Yeah. Basically. Except trying to do it from a radar in a spacecraft, you got to have a hell of a lot more bandwidth.
It's a moving target.
But aside from that, it's essentially the same. Yeah. I described it a little differently. It was a time-varying coherent match filter, but that...
Okay.
Anyway, we were discussing this time and time again. And then the guy that I put in charge of that project was Dr. John Bennett. Now, John had been a grad student of mine at UBC for his PhD. Okay. He was a very capable engineer. He just understood things well. And he'd always wanted to work in this type of thing. He was interested in digital filtering, of which I think a synthetic aperture radar processor is probably the most sophisticated digital filter you can possibly dream up. And so I thought, he's the guy to do it. And he sure was. Anyway, in April of 1978, I remember the days because these were very key issues. I was in Ottawa. I had been on the National Research Council prior to that in the 70s, but I was off by this time. And I met a very eminent physicist that day. I was at the council chambers for something. It wasn't because I was on the council, because I wasn't. I was off it by then. I can't even remember what it was about, but he took me aside and he says to me, he says, John, you have no idea the risks you're taking with it. And then he enumerated all the ways this thing could go wrong. Well, he actually made me a little nervous. So I went back to Vancouver on the Friday of that week. Monday morning, I went straight to John Bennett's office. I said, John, are we ever going to get an image out of this thing? And in his calm way, he said, yes. I said, when? He said, November.
Nice. Okay.
For me, that was good enough.
Yeah.
On November the 28th, 1978, he brought me an image.
Wow.
It was a little tiny one.
But
and
still.
He says to me, he says, you see these wiggly lines on here? Those are creeks. I found them on the map.
Wow. Wow. That's fantastic.
The result was the famous Trois-Rivières image.
Okay.
It was an area around Trois-Rivières in the province of Quebec. And he produced that about a month later. I mean, this thing he brought to me in November it proved that you could make an image.
It could be done.
It could be done.
Yeah, yeah.
And, well, that changed everything. Yeah. Because prior to that, people were trying to do this with what amounted to an optical processor.
Okay.
Fundamentally, what you're doing is making a Fourier transform of the signal that comes back. And you can do that optically. But the quality of the image, I mean, when you first saw the first digital image, MDA produced the first digital synthetic aperture radar image from space. And you there was just no comparison with the quality of the image that was produced optically.
Right.
It was just much better. Right. And we could compensate digitally for all sorts of things that were...
That you couldn't do.
Well, it made it very clumsy to do it with the... and it basically killed the optical processing instantly. In those days, it took us 40 consecutive hours of computing time to produce this image. Wow. But, you know, today they're done in real time.
Wow. Wow.
Or close to real time, maybe half real time or something like that. Yeah. And that led to a realization on the part of the government of the time that this was the way to monitor the North, with a spacecraft with a synthetic aperture radar in it. Because it sees through clouds, it works at nighttime, so you get an acquisition every day. The ice service, the Canadian Ice Service, uses RadarSat 1 and 2 data now to monitor the ice in the north, of course, all year, and in the wintertime in the Gulf of St. Lawrence.
Really? Wow.
And it was clear to us at the time that this was the technology to monitor ice. Because you can tell where the ice is, obviously, but it's more than that. You can get an estimate of the age of the ice. You can tell what type of ice it is, because a synthetic aperture radar basically measures surface roughness. Okay. The rougher the ice, the older it is.
Okay.
And so it is the technology to do it. And along the way, we worked with a company in Calgary, which is called Intera, to develop a airborne version of that of a digital processor. Because at the time, they were I think it was one of the oil companies was drilling up north in the Arctic. It extended their drilling season by a month, and that's huge.
Oh, that's huge. Yeah, that's a big deal.
Because we could monitor what ice was coming down on them. And the weather didn't matter. As long as you get above the weather, and they had a jet aircraft.
Well, and the implications are, you know, from scientific perspective, from a national productivity perspective, for, you know, companies, revenue perspective, employment possibilities, all the different range of
Anyway, the next thing that started was the idea of a Canadian radar spacecraft.
Which became called?
RadarSat, later RadarSat 1, because we came along with a much better one later on. But yeah, that was the origin of RadarSat. It was realizing you could do this, and you could process it digitally. The Ice Service now does, I guess, all of its ice mapping in the north using that technology.
Right.
But back when we were doing this, the way they monitored the ice was a guy in a dome on the top of an old Electra that sort of looked out and drew a map of the ice, you know. I don't know how much per day he could do. But, you know,
I'd say that's a leap forward.
This was an order of magnitude or more leap forward. I mean, so anyway, RadarSat 1 was undertaken. Spar Aerospace was the prime contractor for the spacecraft. We did the processing system. And ComDev was involved with some of the hardware for the radar. And it was launched in 1995.
Nice.
And it's still working in 2012.
Yeah.
It had a predicted lifetime of 5 years. Well, it's well beyond that. I'm trying to imitate it. I don't know how well I'll do.
I think you're doing a great job.
But then we started thinking, it's an information machine. What can you do for a follow-on that maximizes the amount of information the technology is capable of delivering? And that became my little crusade. It led to RadarSat 2.
Okay. And what were the improvements?
Well, there was the
1 and
increase
2?
in the resolution and all that, but that's pretty straightforward. The big thing was to give the spacecraft the capacity to do two things. One was full multipolarization, which means that you not only, you see, RadarSat 1 was a very good spacecraft, a very good radar. But all it really measures is the amplitude of the backscatter from the target, whatever it is. And as I said, that allows you to measure roughness because you get a variety of amplitudes from a small area, and it shows, you know, basically the roughness of the surface. And you can see buildings and all that type of thing. But you can't measure the phase characteristics of the signal with an ordinary radar like was in RadarSat 1.
Right.
I wanted a full quad polarization mode for this thing. And we did it. And you can see ships in a rough sea.
Wow.
Because with a normal straight old radar without the polarization, if you got a rough sea, you get essentially the same magnitude of backscatter from a ship as you would from a big wave.
Yeah.
But the phase is different. Because a wave doesn't have a bunch of corner reflectors on it, whereas a ship does.
Yeah.
You know, where the cabin meets the deck. That's
the angles.
You get a different phase effect
than
you would from a great big wave.
Yeah, for sure.
And so there was that. Plus, at the time, we had this vision that you'd put two spacecraft in tandem near one another. They could measure, use interferometry to measure the height of the Earth to within accuracy of roughly 2 meters.
Wow.
Now, that never happened. They still do it. The second spacecraft was never developed and launched. But RadarSat 2 went up there with a capability to talk to another nearby spacecraft. But what they do now is they use what's called multi-pass, which means that you look at an area from one angle, and sometime later you look at the same area from some other angle, and you use the combination of those two things. And you do it with interferometry again, but to merge the two data sets and create a digital elevation model, which is basically a digital record of the elevation of the land.
Right.
It has some problems.
Do you need two images, or do you have to triangulate it with three?
You can do it with two. Okay. You can do it with more than two. It basically uses an interferometric technique, so you can do it with two. And there's some funny stories about that too, because things that move, of course, cause you a problem with well, sometimes it's a source of information, sometimes it's a problem. Because if you're taking one image on one day and then sometime later you take a second one, if anything has moved, it causes a problem.
Sure.
But you can use it. I'll explain to you how you can do that. But there was this famous story of a building in, I think it was in Milano, in Italy, that had moved. And it was a question of a couple of weeks. Anyway, make a long story short, it fell down a couple of months later. Okay. At least they could evacuate the building. So the other thing you can measure, because if you use interferometry, you can measure millimeter differences.
Wow.
You can watch the land above an oil field slowly sink as you extract the oil.
Really?
Yeah.
Wow.
Oh, yeah.
That's fascinating.
Oh, yeah. And it's those types of things that this spacecraft could do.
Oh.
And it was built to do it.
Yeah.
And that's RadarSat 2.
Wow. Well, and this is around the time when I was actually in the Naval Reserve,
Oh,
we
yeah.
became aware of the technology that we were using with the MCDVs, the Maritime Coastal Defense Vessels,
Yep.
mapping the undersea.
Well, MDA did that too, you know. We were doing a similar thing in the undersea stuff at the same time. And it used a different, mathematically it was different, but not that much different. And it was a way of mapping the undersea very accurately. Yeah. And all of that stuff grew out of something that was really something that I was very proud that we were able to do it. But today, of course, people look at Google Earth, for example, and they take it for granted. You know, you look at your house, and it'll tell you the latitude and longitude to a pretty remarkable accuracy.
Very, very close.
It's not as good as it could be, mind you, but, but it's not bad. You know, it's within a few, maybe 50 meters or so.
Yeah.
Well, that technology, the ability to do that, to take a visible image, do it with radar as well, of course, but to take a visible image and map it onto the Earth's surface accurately was all developed at MDA in the late 1970s.
Yeah.
And in the civilian world, I'm sure the military was doing it just as well. I'm sure we reinvented a lot of the things that they did, but this was now available to anybody. Yeah. The ability to do that. And today, I'm told that about 70% of the processing of Google Earth is done on MDA systems.
Oh, is that right?
Oh, yeah.
Wow.
Oh, yeah. It's we did the precision processing system to solve that problem for the high accuracy processing system in Sioux Falls, South Dakota, which is where the U.S. Geological Survey has their space data processing center. And we did one in Japan at the same time. And did it directly for the Japanese Space Agency.
Wow.
And well, that's really the story of how MDA got into the space business.
Wow.
We built, well, we were responsible, we were the prime contractor for RadarSat 2.
Yeah.
We won the competitive bid. And the competitive bid, what won it for us was this was a measurable advance in capacity. The competition wanted to make a clone of RadarSat 1. My view of that was, well, why the hell do that when you can do something much better? Yeah. And it changed things.
Pushing the boundaries.
Well, that's right. And my reason was that, first of all, the government didn't have enough money to do the follow-on to RadarSat 1. But here you had the ice mappers totally dependent on this spacecraft by this time. The guy in the dome on the top of an Electra was out of a job long ago. and problem the ice service had, was because of all this problem with lack of money in the government and so on, the business of ice mapping, they were now beyond the design life of RadarSat 1.
Oh, okay.
Because, you know, that was the year 2000. We were now into the early 2000s. We still hadn't managed to get this all done. The issue was that the industry had to come up with the money to complete it. The government, I think the number they had, I can't remember what it was now, but I think it was it was a couple of $100 million, maybe 300. I don't remember. Okay. But we had to complete that. We had to provide the rest of the money. Yeah. And in return for that, we got the rights to the data. The reason the company had the rights to sell the data was because we'd paid for a significant part of the spacecraft.
Yeah,
Now that has worked out in the long run.
It's a public-private partnership.
It was a public-private partnership. And you know, MDA's made a good business of making that data available to people. And frankly, what the government got was data at cost for that, you know. Well, the thing became a sort of a semi-commercial venture. The competition was SPAR, and I always regard it as a little bit unfortunate that caused SPAR to sort of unravel. And the reason, the difference in philosophy between the two companies was SPAR saw themselves as a supplier of space technology to the Canadian government. We saw ourselves as a supplier of space-related technology to anybody who would buy it. And that was a big difference.
Yeah. Well, and you have to, in business, you have to be nimble. You have to be able to.
Well, that's right. And you know, one of the things that has amazed me about it, I feel kind of bad about it in a way, is about a year after all this happened and SPAR got basically cut up and sold, we bought the robotics division.
Oh, okay.
Which was the Canadarm.
Right.
And the speed with which that became the MDA arm has always embarrassed me. SPAR did most of the work. They did almost all the work. We did the software for the Canadarm that ended up on the space station. And of course we finished it. But when we had very little to do with the first Canadarm, almost nothing. And of course we took responsibility for the second one, the one on the space station. And I think we did all the software. I might be slightly wrong. It was certainly the majority of it. And overnight, people started calling it the MDA arm. And, you know, we just bought the piece of SPAR that made it. And of course, the company, I should say we, because I'd retired from it by that time. But the company, MDA, has done, the company completed that. Yeah. And it's been successful. It's worked very well on the space station and so on. And we've gotten involved in various applications of that technology, including NeuroArm. I don't know if you know about NeuroArm.
No, I don't.
Well, NeuroArm is an interesting thing. That was done, again, I wasn't here, so I only know peripherally what was done. It was done with the University of Calgary. It allows, it's a little tiny robot that can do brain operations.
Wow.
That's what we call it, NeuroArm.
Okay.
And if you look at the two problems, this huge thing that was on the shuttle in those days versus the challenge of doing it inside a person's head, there's a common requirement to both applications. The person operating the arm cannot see the target. He or she has to see it on some kind of video in the case of the space of the shuttle and the space station, or on an MRI display in the case of the brain.
Right.
It's the same problem. How do you navigate yourself around? Because the accuracies required in the space application, while not in the sort of micromillimeters that you have to worry about inside a person's head, are still quite tolerant, quite precise relative to the size of the instrument itself. And so it's a similar problem in that sense. And that thing is not commercially available yet, but they did an operation with it on a young girl in Calgary. It was very successful.
Wow.
They had to remove, I don't know exactly what the thing was, but I think she had a tumor. And they were able to get in there with this little thing.
So is that at the clinical trial stage? Or?
Oh yeah, it was a clinical trial stage.
Right, okay.
I mean, she was... she's still with us.
Yeah.
and doing very well, apparently. Nice. So you know, it's that.
Those kind of implications of how this technology can benefit us.
Well, it's an example of taking something that had to have all the reliability issues and precision and all that of being able to do this in space, where the operator was in a similar position to what they'd be in the operating room in terms of trying to interpret what's happening as you're doing it, would never have happened if we hadn't had the challenge of trying to do it in space.
Yeah.
Because you see, you have to have a robotics in that case that operates in a weightless environment. And there's all those implications.
Other complexities.
There's all those other complexities, absolutely.
Yeah.
So anyway, that's kind of how MDA got into space. And when that contract was won, that was when I decided to retire. I was 62 by that time, and I thought, you know, I never dreamed I could get this far. Yeah. And it's time. It's time to pass it on to younger people. And that's what I did. Yeah.
But you didn't stop there, did you?
No. I had a 2.5-year retirement, and I didn't die at the end of it. What happened was I became interested. Through my son, I met a very, very, I guess I'd say eminent, a very clever scientist who had been a professor at Moscow State University, which is kind of the MIT of the old Soviet Union.
Okay.
It was basically engineering and science in the same way MIT is. And he had an idea of how to build a new type of solar panel. And we formed a company to do it.
Where do you see the industry for solar panels, for renewables, for a lot of those sustainable industries? Where do you see the future going?
Well, in the last decade or so, I've given a lot of speeches about my vision for the future of energy. I watched the world change during my 40-some-odd years of being in industry. I watched it from space. I saw it happen. I saw the ice melt. I saw desertification spread. I saw cities grow beyond any reasonable size. I think when you look to sustainability, there's a big open question here. Is this planet sustainable? Can 7 billion people sustain some kind of lifestyle on this planet? I think that's an open question.
Well, I think we're going to make that decision, aren't we, by our actions?
Well, yeah. Yeah, we may exterminate ourselves. You know. That's the. That's
keeping the conversation a little more on the
positive side.
Keeping an intention of positivity. What would
What's the answer? The answer, in my view, is we move to renewable energy supplies. It's going to take a long time. I mean, you can't do this overnight.
Yeah.
And the big problem.
But do you see an opportunity there for young people especially?
Oh, absolutely.
I mean, I think if you were a young kid in school today,
that's where I'd go.
Okay.
You know, I went into electronics when I was a teenager. I went into space when I was in my 40s. Because that was where the excitement was. That's the reason I went. I didn't have any great vision of where this was going to lead me. But it was just something I wanted to do. I counsel a lot of young people, and I give them one piece of advice. Enjoy what you do at your job, and you'll be successful. Yeah. If you take a job because it pays you a lot and you don't like it, you won't be successful.
No, that's true.
And
just one of the
you're very unlikely.
The truisms of life, isn't it?
Well, it is.
Yeah.
And I think for young people, that's the thing. And for me, gee, electronics in the 1950s, that was where it was at.
Sure.
Computers in the 60s.
Yeah. Well, and
space in the 80s and 90s.
You didn't know when you stepped out on that path, you didn't know that you would be successful.
Oh, heavens no.
You didn't know if you would be successful. You didn't know that you would be as wildly successful as you have been. But you moved in that direction with that intentionality.
And you know, the most important thing you do is pick the people you work with.
Oh, yeah.
You know, because, I mean, I always have to have somebody who looks after the day-to-day running of a company and making sure it has enough money to survive the next day.
Yeah.
I'm the visionary. Yeah. That's my skill, and that's what I do. And I let somebody else make the final decision. Mm-hmm. Because, you know, you got to be able to afford it. And there's lots of things I've thought up that we didn't do.
Yeah, I'm sure.
But I think, to get back to sustainability, I believe the most important thing is to address the energy issue. Everything else follows from that. I think, frankly, the system will evolve towards distributed generation. But that wasn't possible in Edison's time, but it is today. Computing technology has made it possible. So there's all these things that we can do, but we've got to have the foresight and the commitment to begin to do it, so that we can learn how to make our energy supply 100% sustainable. And
that sounds like a nice vision for the future.
Well, I think
how would UNBC be a part of that?
Well, I think UNBC can be a part of that, and we do talk about it at this stage, because it sits right in the center of probably one of the biggest renewable energy supplies in the world.
Yeah.
You know, you go over to Haida Gwaii, you got tidal, you got stuff there, and you go up north, you've got all kinds of biomass, you've got natural gas galore. I think that we certainly have an opportunity to lead.
Yeah.
And you mentioned it before. The doing it leads to an export business because there's going to be a demand.
Oh, yeah.
If you take the approach that the energy industry retains the same structure it's always had, I think mostly of the electrical side of it,
yeah.
I don't think you're thinking in an innovative enough way to address the issues of the future. You've got to think outside the box.
Order of magnitude change.
It's an order of magnitude change in the long run.
Yeah.
And frankly, in my view, the time has come when we have to start figuring out how to do that.
Yeah.
Seriously, not just say, oh, well, you know, solar doesn't work at night and whatnot, but actually figure out the system problem. How do you take this hodgepodge of intermittent sources and make firm energy from it?
Well, and it's systems thinking. My big thing that drives me crazy is traffic lights. Traffic lights, to me, they're more than a nuisance. They sap the productivity of our nation. They sap the time of our people to be at home with their family, or time that they could, you know, they sap resources, obviously, because we're paying for brakes and fuel and everything else to sit at them. You know, and my systems thinking mind just says, well, why don't we re-engineer the whole system so we don't build more. We need to get rid of lights. We need to actually, and we can. But if we design an intersection,
you design it with overpasses.
Exactly, an overpass, and then feeders, right? So nobody stops.
or very seldom stuff.
We very seldom have to. Actually
Well, yeah, I can see that. Whether
and what if we did? But what if we did that everywhere? It's not going to happen overnight. But what if we started to do that?
I think that sustainability television has a very important mission, which is to help educated people, particularly young people, in the importance of sustainability in a planet that happens to have 7 billion human beings at the moment, which may be too many, and is educating people as to the importance of sustainability of the planet's resources in all their forms. Because our current way of doing things as humans is not sustainable.